Welcome everyone to session 5 of the UCR-UAS's Arduino workshop series for spring 2021. And this is actually our finale for the series. So we're going to be kind of giving a debrief on the final project, which is the main focus of our previous session, and then giving you some extra applications for Arduino, which hopefully be pretty interesting. Before we get into all of that, we have this week's announcements, which I'll let Train take care of.
Yeah, hi. So I'm the Operations and Outreach Specialist for UCR-UAS, and this week we have some announcements. We have the first ever annual banquet coming up on Saturday, May 22nd from 4 to 6 p.m. We'll be just having a US year in review. We're going to talk about our future plans for next school year in person. We will review our new leads and boards, and we'll show appreciation to all of our donors this past year. We will also have a fundraiser raffle for a chance to win 2 Amazon gift cards for $25. So please visit our website for more information on how to attend and how to RSVP. So see you there, guys.
Okay, thanks, Train. So first thing I want to do is show off the final project in action one more time for those who did not see it during session 4. And I'll be doing this in Tinkercad. So I have the familiar circuit for the final project right here, along with this sample solution code, and all of the code for this sample solution will be available on our project GitHub repository, or not, our workshop GitHub repository, and so you'll be able to look through it whenever you need to. So first, let's revisit the goal of this project. So we're trying to create a mini game, or kind of arcade style game, that can be played just using the LCD screen as the kind of interface, and then a single button as the controls. So if I start this circuit, you'll be able to see we have the player character, first of all, is on the left side, and the player interacts with the button in order to move the player. So each time the button is pressed, the player switches which row on the LCD that's on. And the goal for the player is to dodge these obstacles, which are starting on the right side of the screen and moving to the left. It's supposed to be an endless runner game, so the obstacles will keep coming over and over again in randomized formations. It'll keep going until the player character collides with one of the obstacles, at which point the game resets. Provide extra feedback to the player about their score, which is basically how long they survived, as well as how many games they've played. We use the serial monitor and just output that information at the end of each game. So some of the topics that we learned in previous sessions that we had incorporated into this project include how to use the Arduino to detect whether a button is being pressed. That was something we went over in session 0, which is the introductory session. And then how to use a state machine with this sensing mechanism in order to use the button to control things. Basically, whenever the button is pressed down, you can make something happen. In this case, it's switching the row that the player character occupies. And state machines we introduced in session 1 and kind of expanded upon in future sessions. The serial monitor was introduced in session 1, and we learned how to do timing in the context of a light show in session 2, and the same timing concepts are being applied in this project, although in a bit more complex way, because there's a lot more things to keep track of and basically to set the time interval in between when actions take place. And in session 4, we covered the LCD, how to use the LCD component, as well as the liquid crystal library for Arduino. We covered those before diving into the final project, and this is of course very integral to making the project function. Now, I want to bring something to your attention if you've were able to finish the project, or you're just interested in looking more into it. In the template code, were these game parameters set up, basically using the define preprocessor directive that we covered back in session 2. We were able to basically make an alias that we can use to refer to whatever quantity or value we want to put here, and then reference it in the code so that whenever we change these values, the code will program will reflect those changes. And you can actually tune the difficulty of the game using some of these parameters. So for example, I can increase the number of max obstacles, and then if I run the code, then now it's able to now it can spawn up to 4 obstacles before waiting for one to go off the screen. But at this point, it's kind of hard to see that, because by the time force obstacle is spawning, the first one has reached the end of the screen. So you can also tune the delay between objects moving and the delay between objects spawning. So for example, I can make it a 400 millisecond delay between spawns, and if I run again, now there's going to be 4 obstacles on the screen consistently, and this makes it more difficult than it was previously, because now there's a basically constant stream of obstacles. And you can also make the game easier by making sort of the reverse changes to these parameters. So if you want to experiment with the game further, and that's something you should look into. Now, I also want to go over the parts of the final project, like the actual coding part, which I feel people probably had the most trouble with. And I'm going to open up okay, I've got a question chat here. So obviously, when I was explaining how to do the code for these functions, I was assuming a very specific way you would want the game to operate. Like, for example, having each obstacle spawn on a random row. But if you wanted to change how the game operates, you would just need to change how you coded these functions. So you could make it so that obstacles are less likely to have a long line of obstacles on the same row by basically keeping track of how many obstacles have spawned on the same row and automatically spawning on the opposite row if that number amount gets too large. And these are things you can do by just tweaking how you code the main functions. If you want to make it really interesting, you could and you know a bit about C or C++ programming, then you could also modify the helper functions, which could allow you to do even more. Although really, there's a lot, because of how these helper functions are set up, there's a lot you can do without having to modify them. Honestly, like you could have the player start in the middle of the LCD screen. I mean, you couldn't have them in the exact middle, but like in column 7 or 8, for example, and then you could have obstacles spawn on either side of them and move towards them from either side. That way, and that would make things more challenging. Because for one thing, you can have even more obstacles spawning at once, because now there's 4 positions where they can spawn from. So even though this is a very simple concept, there's still a lot of ways you could tweak it to make it more interesting. And hopefully that gives you an idea of where you could go in terms of customizing the project. So back to the code review. I'm going to be doing this from inside the Arduino IDE, just because the font is bigger here. So I'll be limiting this in-depth walkthrough to the functions move player, move obstacles, and spawn obstacle for the sake of time, since I'm going to be giving a demo during this session along with this review. And unlike some of the other functions, things like the game setup function or game over function, where you're basically just cleaning up or setting up variables. These three functions involve a fair amount of logic, so like if statements or for loops, and that probably made them more challenging to implement. So the first function we'll take a look at is move player, and this function revolves around a state machine, and as such you'll likely want to make a variable to store the state of the state machine right off the bat. In this case, I made a static variable last state, but you just as easily could have used a global variable, and you wouldn't have needed to modify any of the other code in the function in the solution to do that. So in this state machine, we determine the next state based on the previous state of the button, which controls the player, and that is stored in the variable last state. And we also use the current state of the button, which we find using digital read, in this case on pin 7. That's the pin that the wire connected to the button is on. Here I made the switch statement operate on the value returned from digital read rather than the value of the variable last state, because that simplifies the logic. In the case that digital read returns 0, we know that the button is currently pressed. And if the button was previously not pressed, that means that the user just pressed it. So we need to move the player character. If you need to brush up on how the switch statement works, by the way, we covered that in previous sessions, I believe. It was mainly in session 2 where we covered the switch statement in relation to state machines. So the procedure that I use to move the player character is first to clear the old position of the player character, which these two lines accomplish. Then we update the player character's position in the struct that represents it, which is what this line is doing. And then we write the corresponding character in the new location on the LCD. And that's these two lines. I guess the indentation here got messed up. It's supposed to be like that. So note how each time I reference a property of the player character, such as its column or its image, I use the value stored in the struct called player. Or that's the instantiation of the entity struct that we're using. And when I do that, even when I know that the value will not change during the program, like for example, the player's column is always going to be 0, because that's how we basically programmed the game with that in mind. And so the only way that would change is if we actually altered the program itself. And basically, we want to ensure that even if those assumptions change, then the code should still work. So even if we decide to move the player somewhere else to a different column, we could still use this code to make them switch rows when the button is pressed. Now, the other thing we need to do when the button is first pressed is to set last state to the button down state. so that when we come back to this state machine, we will not think that the button has been pressed a second time. This is necessary because in the time it takes for the user to push down on the button and release it, the move player function will be executed several times. In the case where digital read detects that the button is not being pressed, we know that we don't need to do anything with the player character. However, we do want to set last state to the button up state in case the button is just being released. Since this behavior is fine to use whenever the button is not being pressed, we can just make it the default behavior in the switch statement, so it'll execute unless this specific case is satisfied, which is when digital read returns 0. So that's all for the move player function. Next, we have the move obstacles function. This one is focused around looping through the 2 arrays that store the locations of obstacles and updating their locations as you go in order to move them 1 space to the left. Specifically, the arrays, which are defined here, are called row 0 entities and row 1 entities. And as you would expect, they correspond with the top and bottom rows on the LCD screen, respectively. You'll need at least 1 for loop for iterating through the 16 positions in each array. You can manipulate both arrays in the same for loop like I did, or you can use separate for loops. What I do before trying to call the helper function set obstacle position is check whether the pointer at the current position in the array is a null pointer, which means that there's no entity in memory associated with it. You might not have known about null pointers if you aren't very familiar with C or C++. Fortunately, this check isn't strictly necessary because set obstacle position is designed to check for null pointers anyways. So it's perfectly fine if you got it working without this check. Now the next if statement, however, is very important because it checks for an obstacle occupying the same position as the player, which must trigger a game over. So we check 2 conditions to determine if the obstacle is moving onto the player's space. One is whether the column of the obstacle matches the column of the player, and the one is whether the player is on the row matching the array that we are looping through. If both of these are true, then we call the game over function that is implemented later on in the program. And then if not, we move the obstacle by calling set obstacle position, where the new position is 1 column to the left of the old position and on the same row. And I went over why we would be using these arguments in session 4 to make it move to the left. So this same process is repeated for both arrays, except when you're looping through the row 1 entities array, you use 1 for the row of the obstacle instead of 0. So like you can see right here, compared to here, we just replace the 0s with the 1s. And finally, we have the spawn obstacle function, which is actually the shortest function you need to implement, assuming your implementation is similar to mine. First, we must verify that the current obstacle count is less than the maximum allowed before proceeding, which is done on this line. If it is not, then we just return. If we will be spawning an obstacle, then we need to determine a random row, and to do that, we use the random function, just like I explained in session 4. Then we need to choose the add obstacle we need to use the add obstacle function to attempt to add an obstacle to the row that was just randomly selected, and which I'm storing in the variable row here. Since the add obstacle function will return false if the obstacle could not be added, I'll take advantage of this by returning only if the spawn was successful, and otherwise trying to spawn an obstacle in the other row. If you did not implement this extra check, your program will probably still work just fine unless you've made the spawn delay so low that it's trying to spawn obstacles before they have a chance to move. Like spawn multiple before the first one you spawned has had a chance to move out of the way. So that covers the in-depth look that I had planned for the final project. And of course, you can see the solutions for all the other functions in the sample solution on the GitHub. So with that out of the way, we can actually, I have one more thing on the final project. We'd like to get some feedback on this project to help with planning potential future workshops. So mainly, we'd like to know if this project is the kind of thing that you'd like to see again, and if you think it could have been done better. So I guess also more in general, tell us if you'd like to attend a workshop like this in person, and like what things you might want to learn in such a workshop. And to give us this feedback, you can just put it in the comments for the sign-in form for this session. Now for the rest of this session, I'm going to be diving into how you can integrate an Arduino application with other software in order to do more and give yourself more options. What I'll be demonstrating here is something that you need a physical Arduino board to do. So this will be more of a lecture than something you can follow along with. So you can just sit back and watch for the rest of this session. Also, as a heads up, I'll be turning my camera off partway through this demo, and the reason why is that I'll need to have my Arduino board plugged in. My laptop doesn't have enough USB ports to fit it along with everything else. So let's see, the ability to hook up sensors to an Arduino board, along with the abundance of existing libraries to make interfacing with them easier, is one of the reasons why Arduino boards are currently so popular. But when it comes to visualizing the data collected, the serial monitor will often be insufficient because you'll want to be looking at trends in this data over time, perhaps, and with the serial monitor, it just gives you can really just get a line by line, or you can try using the serial plotter, which is a feature we haven't really talked about in this workshop series. But even then, you aren't able to like save your data and analyze it later. So we want to see how we can use other software along with the Arduino board in order to give a better analysis of our data. Some software that can help us here is MATLAB, along with its companion software Simulink. For those of you who have not already been introduced to MATLAB, it is a scripting language that specializes in processing data efficiently. Simulink is a modeling and simulation software packaged with MATLAB. It uses a block diagram aesthetic to lay out the models used to process data. At UCR, MATLAB is involved in the curriculum primarily for engineering majors. mainly electrical engineering, computer science, and mechanical engineering, although other majors may receive some exposure to it. It's a powerful scripting language and well worth learning if you're going to be processing large data sets. For this session, we'll mainly be focusing on how to get data into the MATLAB workspace, and we'll be using Simulink to do that. Now, the method that I'm going to be showing you is basically something that the EE team at UCRUS developed over the past year to basically allow us to log the data we get when we're testing a motor. And I'm going to be showing you how we went about logging data from two different sensors independently, or like simultaneously, I mean. And it's all coming through a single Arduino board. And basically, I'll be showing it off using a sample program that just produces, like mimics a sensor by producing random numbers. But you should be able to see how it would apply to a situation where you've got physical sensors connected to your Arduino board. So before we get our data into the MATLAB workspace, we'll be putting it into Simulink, and to do that, we need to establish a serial interface between Simulink and our Arduino. The serial port that the Arduino board uses to send data to the serial monitor can also be opened by other applications. In Simulink, there's a set of blocks added by the instrument control toolbox that's used for communication over serial ports. So it's a very convenient to use this to receive the data. You can see some of the blocks in the image on the slide. The serial configuration block defines how the Simulink model will communicate over the desired serial port. The serial receive block outputs data received from the desired serial port, and the serial send block sends data from its input through the desired serial port. For this demo, we will focus on just receiving data from the Arduino, which only requires the serial configuration and serial receive blocks. There are some settings you will need to set for both of these blocks before you can get started receiving data. And I'm going to show you in Simulink what it looks like to set up these two blocks. So I've got a Simulink model here that right now just has the serial configuration block and the serial receive block. So these blocks are actually already set up, and but I'll be going over the options you can do. So actually, I'm going to need to plug in my Arduino board now so that these blocks have something to connect to. So I'm going to be stopping my video. Just hold on a second. Okay, now it's in. Might need to give it a chance to notice the COM port first. Okay, now it sees it. So first of all, of course, you'll need to set the serial port, and you'll need to do that in both the blocks. So the serial configuration block that's set to a specific communication port will be controlling any of the other serial blocks that use the same communication port. And also in the serial configuration block, you need to set the baud rate, and this needs to be the baud rate that the Arduino is communicating at. And we're going with the same one we've been using throughout these workshops, 9600. And then that's all there is for serial configuration block. In the serial receive block, there's a lot more options that you may need to set. First is the header and terminator characters, which will be used to identify the beginning and end of transmission. All of the data that the receive block will output needs to be received in between a header character and a terminator character. You could use almost any character as your header, but your terminator needs to be one of these 4 options. So it can be carriage return, line feed, which is also referred to as a new line character. You could do both carriage return and line feed, or you can use the null character. For this demo, we will use the capital letter G as our header and the new line character as our terminator. Okay, so next, data size is how many values should be in each set of data received, where each set of data is just whatever is in between your header and terminator characters. So if the data size is just 1, then the receive block will be expecting 1 value to be sent between each header and terminator byte. I'll show you what sending multiple values look like later in the session. The data type is how the data received should be interpreted. If we'll be sending an integer value from the Arduino, then we will need to choose either int8 or int16, since in the Arduino Uno, integers are represented using up to 16 bits. If we will be sending a float value, which I'll be showing later on, then we need to choose single instead. Next is blocking mode. You can enable blocking mode to make your simulation pause until the serial receive block has received enough data to update its output. In order to keep your simulation running smoothly, I'd recommend not using this mode. You can have the serial receive block output a certain value when no data is being received. So it could be a custom value or just whatever the last value it output was. And for our purposes, this isn't going to matter, since I'll be showing you a method to guarantee that only new data samples get recorded. Block sample time should be set based on how often the Arduino will be transmitting data. For now, we'll have it set to sample once every 100th of a second or every 10 milliseconds. So that's it for the serial communication blocks. Now that we've got data in the Simulink model, we need to transfer it to the MATLAB workspace, because otherwise all that data will go away once your simulation ends. So we're going to save our data to the MATLAB workspace using a toWorkspace block. We'll be saving our data as a time series, although there are other formats which may suit different purposes better. And this here is an example of what the toWorkspace block looks like. Realistically, it's often important for us to know how much time elapsed between our samples or between changes in whatever data we're logging. In order for this to be reflected in Simulink, its internal clock must be synchronized with the real-time clock, so it accurately tracks how much time is elapsed. There's an add-on for Simulink called the Aerospace block set, which contains a block that can do this, called the set pace block. Using the set pace block, you can choose how many seconds on the simulation clock pass for each second in real time. So you can have time pass at half speed or double speed if you want, or you can make it a 1-to-1 ratio as we have here to synchronize the clocks. This way, if 1 second elapses between two data samples, this will be reflected in the time recorded in Simulink, and that time will be available with the data that gets sent to the workspace. If we want the MATLAB simulation to run in real time, that means we can't have the serial receive block in blocking mode. And as I said before, we probably wouldn't want it in blocking mode anyways. But if we don't use blocking mode, then much of the time we may have no useful data to output, and this will clutter up our data logs if all these extra data values are being recorded. We could go in after the data is collected and remove all the entries where there's no new data, but it'd be better if we could prevent those entries from being recorded in the first place. You may have noticed that because we have blocking mode disabled, the serial receive block had an additional status output in to go along with its data output. This outputs a logic signal, which is 1 if there's data available and 0 otherwise. We need to use this signal to control when the two-workspace block activates, but the two-workspace block does not have any enable input by itself. We can, however, put the two-workspace block in its own separate subsystem that only runs on time steps where the status signal is a 1. A subsystem that must be enabled by a logic signal is called an enabled subsystem in Simulink. An enabled subsystem, like any other subsystem in Simulink, can have an arbitrary number of inputs and outputs. Since we just want to save data to the workspace from inside the subsystem, we need as many inputs as needed to bring in the data, and we don't need any outputs. So these images here, the one on the left shows data entering the subsystem from the outside. You can see from this arrow here, the source of the data is cut off in this picture. The image on the right shows data entering from an import inside the subsystem, which is labeled with the number of 1, which corresponds to the number 1 here. So data coming in from the arrow is coming out of this port. Also note how the image on the outside of the subsystem serves as a preview of what is inside. And now I'll add the blocks we just covered to our Simulink model. So to add more blocks, I'm going to go into the library browser. First, let's add our set pace block. You can find that in the aerospace block set here. It's under animation and animation support utilities. And it defaults to a 1 second per 1 second ratio, which is what we need. Next, let's add the enabled subsystem, which is under ports and subsystems. Inside of this subsystem, since we don't need an out port, we're just going to remove that. Then we're going to replace it with our two workspace block, which is under syncs. The settings default to saving as a time series, so we won't change that. We can also set what name is used to reference your data once it's saved to the MATLAB workspace. For now, we'll just leave it as SimOut. So now our Simulink model is set up. And now we need to set up the Arduino program that will be sending the data, basically our mock sensor values. To start off, let's just send a constant value, for example, the number 1, at a rate of once per 10 milliseconds. So you might be thinking, all we need to do is call serial.write1 over and over again with a 10 millisecond delay in between. But if you remember, we had our serial receive block set to expect a header character and a terminator character. So it's going to be expecting each individual 1 we send to be preceded by a header character, which in this case is a capital letter G, and then followed by the terminator character, or the new line character in this case. We're going to need to program the Arduino to send these bytes along with the actual data. So let me do that right now. I'll make a fresh Arduino sketch. So first, because we're going to be using the serial port to send this information, I need to set up serial communication, remembering to use the same baud rate we set the serial configuration block at. Then I'm just going to write each part, first the header character, then the data. We want to use just the number 1 here, not the character representation of 1, because it's going to be this is going to be interpreted as a integer value. In our new line. Finally, our delay. Now I'll upload this. And then we can run our Simulink model. I have it set to run for 5 seconds. It might take a bit of time to start up. So now if we go into the MATLAB workspace, we have this out object here. And we can access, actually I have a slide on this. So once the simulation ends, we'll have the object called out, which contains all the data from your 2 workspace blocks. See the data recorded under the name SimOut. We can enter this command into the MATLAB command window. And then to see the timestamps for each data point, we use the same command but replace data with time. Basically, these are 2 separate vectors stored within the SimOut object. For data, it's just a vector of ones, since the Arduino is just sending one over and over. If we look at the timestamps, have basically it's incrementing by 1/100th of a second, because the Arduino is transmitting values at a rate of 1 every 10 milliseconds. And here we can see that the first value is actually received after 1 second and 340 milliseconds. So now we've seen that the basic model works. Let's try modifying it to make it more realistic conditions. So if we're trying to collect some sort of sensor data, oftentimes it will not be an integer value. Rather, it will be stored as a floating point number. Floating point values are stored differently from integers, but we still need to send them as individual bytes. So how do we send a floating point number as individual bytes and still get the receiver to recognize it as a single number? Well, the C or C++ programming language basically both provide methods for you to represent the same data in memory in multiple ways. One of those methods is by creating a union, and a union occupies a fixed amount of space in memory and allows you to store different things in that space. What those things are is up to you, because you specify them when defining the union. The important thing is that you can switch how the data in that location in memory is interpreted during runtime by choosing from one of the data types you specified. Accessing the data in this way is performed like accessing the members of a struct, so you would use the dot operator. So how does this apply to our situation? We need to store a value as a float and then interpret it as bytes, and the following union accomplishes that. So the two options we have for interpreting the data in this union is as a float using the name val, where a float is stored as using 4 bytes, which basically taken together give the floating point representation of the number. And the other one is an array of 4 8-bit unsigned integers, which is basically just 4 bytes. And so each one of these could individually be sent over the serial port using serial.write. So basically, when we store 4 bits in this union, we can then at any time interpret them as either a float value or array of 4 distinct bytes. So once a float value has been stored in the union, accessing elements in the array of bytes will return the corresponding bytes that are used to store the float value. Hence, we can send the 4 bytes in order using serial.write, and the serial receive block will use them to reconstruct the float value as long as it was set to receive values of type single, which is the MATLAB equivalent of a float. In other words, it occupies 4 bytes in memory, just like the float does in the Arduino code. And then this here is the for loop that we use to send the float value. Basically, we start by sending the byte index 0, and then we work our way up. So now I'll demonstrate this. I'm going to be using a pre-made Arduino sketch for the sake of time. Also a pre-made Simulink model. I'm going to upload this. And this is what we're going to be, the model we're going to be using. Similar to the previous model, except I've got this display here, which will tell us what values are being sent through the data output. And then inside the enabled subsystem, I have a second to workspace block, which is basically going to be recording a 1 whenever the data received was less than or equal to 0.5 and a 0 if it was greater. So our sketch should be uploaded now, and we can run this program or run the model. You can see we've got values showing up on the display. Now if we go into our workspace, we can, and because we're using different names in the to workspace block, I have to make sure I reference these names to access the data. So out dot current value dot data. And so we get this column vector here, and then we can get the time as well. And then we've got the less than half data as well. We see we're getting 1s and 0s depending on whether the value in current value dot data was greater than 0.5 or not. So I have one more thing to add to the our Simulink model. However, we've reached the hour mark for this workshop, but I guess I'll keep going here just in order to complete it. It won't take too long. So being able to log a single value in real time is useful, but we're able to do a lot more because the serial receive block can receive multiple values at once. In fact, it's as simple as having the Arduino send both values in between each header and terminator and updating the data size parameter in the serial receive block. For each additional value that you want to receive, you need to increase the count in the array for data size. Increasing the data size beyond one value will automatically convert the data output from the serial receive block to a bus with the required number of signals. This bus will allow both values to be sent as one signal. The main limitations to receiving multiple signals from a single serial receive block is that the signals must use the same data type and they need to be sent at the same time. So I have another Simulink model. That's the same one. Okay, this one serial receive block has had its data size updated. So now instead of just having the number 1 by itself, we have the number 1 followed by the number 2 in these brackets. And you could keep increasing that count if you needed to. And then one other thing is you can log your two data values together by keeping them in the bus, or you can separate them out and log them independently. If you want to separate them, then you'll need to use a demux as shown here. And keep in mind that the top output from the demux is for the first value that was received, and the bottom is for the last value that was received. So now I'll demonstrate this. First, I have to upload the code for sending 2 floats. So this code is basically doing the same thing as that previous one, except now there's 2 of these unions. Each one is given its own random value between 0 and 1. So now we'll run this model. You'll see in this case, both values in the display will be changing, and it'll be 2 different values. Okay, let's quickly take a look at our data. So in this case, it's actually giving us a 1 by 1 by 71 vector, which having the extra dimension there might be a hassle. So what you can do is use this function squeeze on this vector, which will give you the same column vector that we had before. And then you could do the same with second val. And something to remember is that because we're having both these 2 workspace blocks sample at the exact same time, the time vector of timestamps you get from one of the 2 workspace blocks will be the exact same as the one set you get from the other 2 workspace block. So basically, if you need to compare but the values from these 2 workspace blocks to the time when they were collected, you can just compare them both to one of the timestamp vectors. And that wraps it up for our data logging demonstration. One more word on this is a more practical example to give you an idea of how this has been used in the past is when we are testing motors, basically we have a load cell that is measuring the thrust that the motor produces because it's got a propeller fixed to it, and then another sensor that can allow us to record the RPM. And basically you can't see the Arduino because it's hidden here, but it's hooked up to these two sensors and recording data in real time. And basically it does some preliminary processing of the raw output from the sensors in order to get numerical values. And then those numerical values are being transmitted through the serial port to a computer, which is running a Simulink model that involves that, includes that enabled subsystem and all that, which is tracking the values received. And so when we're running this motor, we're getting real-time output that is also being saved to the MATLAB workspace for us, so we can keep all of this data, basically format it in a nice spreadsheet, and then save it for later. So hopefully you can kind of relate this to like how it could be useful for your projects. It might give you some inspiration. Oh. All right, so that's all I have for today, which means we've reached the end of the Spring 2021 Arduino Workshop Series. I hope everyone has gotten some inspiration from these workshops and will be able to put their knowledge of Arduino and C++ programming to good use. As I said earlier, we may host future workshops on topics similar to this, so any feedback that can help us improve would be very important. Thanks everyone for coming.